Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In this video we will learn about relationship between electric field and electric potential. By now we have covered a lot of cases of electric field and electric potential, and here we will be exclusively watching or learning the relationship between these two. Now one of the relation of V is we have already talked about, that means potential is defined as minus integration of E dot dr. So that's basically a relation between E and V, and this says from infinity to any location which you are interested in, so that's a potential at any point. In this particular relation we have taken infinity as our reference location, and if E is a function of R, we can place here and we can integrate and calculate the potential. So idea is, if the electric field is known, we can find the electric potential, or in other terms we can say, if the vector field is known, we can find the scalar field. So both the fields are linked to each other. Now sometimes we will be given this E in the form of I cap j cap, because that's a vector quantity, so it might be given this term like Ex I cap plus Ey j cap and Ez k cap. So Cartesian coordinate system may be provided. So if E is this, we can write dr as vector, which is equal to dx I cap plus dy j cap plus dz k cap. If you are thinking how we are writing, so that's quite easy to understand, because r vector as a position vector can always be written as xi plus yj plus zk. If we differentiate both the sides, so it becomes a differential r vector is equal to differential x I cap plus differential y j cap plus differential z k cap. Now we know the dot product that has to be performed over here. So if we place E and do dot with dr, so we know the I coefficients get multiplied, y coefficients get multiplied, and z coefficients get multiplied. So using this we can have expression V is equal to minus integration running from one location to another, whatever the locations are given to us. We can say it's going to be Ex dx plus Ey dy plus Ez dz, and this minus sign when enters, so this will make minus integration Ey dy, and then this finally will make Ez dz. So if the Cartesian coordinate system is used, we can use this as expression to find the electric potential out of electric fields. Here in the first integration we need to place the limits of variation of x. So initial value of x to final value of x, initial value of y to final value of y, initial value of z to final value of z. So what the initial locations are going to be, that will be the reference potential, right? So this will become the formula for relation between E and V. If E is known to us, we can easily find out the value of V, or if it is given in the form of r cap or radial coordinates, so we can use this as our expression, which is a relation between these two fields, scalar and vector fields. We have already talked about this is the potential with respect to reference infinity. If this is not the case, then we can write V of any point 1 minus V of any point 2. That means it's a potential difference between point 1 and point 2. This is equal to minus reference location 2 to 1 E dot dr. So if we are putting the limits, which is not infinity, starting limit, so this left hand side will indicate as a potential difference, and the right side will have a limits accordingly. So this will become the expression for relation between E and V when the reference is any general point that may or may not be infinity. So this is called potential difference. So So these all expressions are indicating if the field is known to us with respect to infinity, we can find the potential at any point. If the field is known to us in terms of Cartesian coordinates, we can find out the potential. If the field is known to us and we need to find the potential difference, we can use this expression. So this is finding out potential out of electric field. Now this relation is also available otherwise. That means if the electric potential is known to us, we can find the field. So how that goes, let me describe there. So we can say this Ex, the component of electric field along the x direction, is minus del V upon del x. That's partial derivative of potential with respect to x. Similarly, Ey can be written as minus del V over del y, and we can write Ez as minus del V over del z. That means they are the partial derivative with respect to the quantities mentioned. In general, we can write E as minus del V upon del r if V is a function of r is the distance from the central or origin location. So if it is in the Cartesian coordinate system, we will be using this. If it is the polar coordinate system, we will be using this. Now if we combine this Ex, Ey, Ez to form this electric field, total electric field E, in this manner, so we will get E vector as, we can take this minus sign outside, and within the bracket we will find it's going to be del V upon del x I cap plus del V upon del y j cap plus del V upon del z k cap. So if we know these individual components, we can place here, sum them up to get the final expression for electric field. So that expression will be used to find out the potential if the electric this expression will be used to find out electric field if the potential as a function of Cartesian coordinate system is known. And we can use this expression to find out the electric field when the potential is function of only radial direction, right? So here we have talked about two types of relations, or rather both ways relations. First was to find the potential when the field is given, and the second is to find out the field when the potential is given to us. Now we will take a few examples to illustrate the application of the first relation as well as the application of the second relation. So we will start from the first relation. So let's move ahead. So here's an example of relation between E and V, and this is more than an example. It's going to be a formula, and that talks about potential difference due to infinite linear charge. So let's say this is infinite linear charge density is lambda is uniformly charged, and there are 2 points 1 and 2 at a distance r1 and r2 respectively from this linear charge as shown in the figure. Now we have just understood a relation, that means potential difference, if we call it as a V1 minus V2. So this potential difference is written as minus integration from 2 point to 1 point E dot dr. So this relation we need to use, and we can find out what the potential difference is going to be. We know in this case of linear charge density or distribution, the field formula is twice k lambda upon r, and we also know this field is in the r direction, that means radial direction, so we can call it as r cap. Carrying this forward, this is going to be integration, this 2 has a limit r2, so we can call it as r2, and 1 has a limit r1 or distance r1. E can be written as 2k lambda upon r and dr, and we will have this r cap dot r cap, because dr, as we know, is dr vector is dr r cap. So this unit vector and the same unit vector dot product is 1. Then this integration will be equal to minus 2k lambda, which will be outside, and this will be 1 upon r dr. We know 1 upon r integration leads to ln r, so this will going to be ln r, limit will be from r2 to r1, which further can be written as minus 2k lambda ln r1 minus ln r2, which we can write it as a minus 2k lambda ln r1 divided by r2. So this is v1 minus v2. Now since r1 is greater than r2 in the picture, then we can think of this entire term is positive, and this minus sign will make entire term negative. That means v1 minus v2 is a negative. Since v1 minus v2 comes out to be negative, which implies v2 is greater than v1. So from here we can have one implication that v2 is more as compared to v1. That means if we are closer to the charge, the potential is higher. If we are far apart, potential is lower. So potential difference, if we want to write, we can write in terms of v2 minus v1. So v2 minus v1, that's a potential difference due to a linear infinite charge distribution, which is going to be twice k lambda ln r1 by r2. So if we remember this as a formula, then we can answer some questions in which this potential difference is being asked due to a linear charge distribution, right? So that becomes an important formula, and as well as use of relation between E and V. We can also see another example, and that will also be a formula, an important one. So this is potential difference due to large charge sheet. So this is infinitely charge sheet of charge density which is uniform sigma, and there are 2 points 1 and 2 respectively, r1 and r2 distance away from the charge sheet, and then we can use that relation, the potential difference, which is v1 minus v2 is going to be equal to minus integration from 2 to 1 E dot dr. Now we know the field because of a charge sheet that we have already talked about. It's going to be equal to E is equal to 2 pi k sigma, and which we later on have written as a sigma upon 2 epsilon naught, and this is going to be, if this is a sheet, so this is going to be in the I cap direction, which we can write as a sigma upon 2 epsilon naught I cap direction. And here dr is going to be simply dx I cap. So this will convert into from 2 point, which is r2 limit to r1 limit, and it will become sigma upon 2 epsilon naught, and this will become dr or simply dx, and we will have a I cap dot I cap, because in this case dr cap will be a dr vector will be dx vector, which is dx I cap. So I cap dot I cap will become 1, and this will turn up as minus sigma upon 2 epsilon naught, that's a sigma, and integration of dx, and this integration runs from r2 to r1. We know this dx will become x, then it will be difference of these numbers, so this will become minus sigma divided by 2 epsilon naught within the bracket r1 minus r2. So r1 minus r2 is going to be positive number, so here it says again v1 minus v2 comes out to be negative, which further implies v1 is less than as compared to v2. That means v2 is bigger. So if we want, we can write in that in the term of potential difference, which is v2 minus v1, potential of 2 minus potential of 1. This is going to be equal to sigma upon 2 epsilon naught, and the distance between these two, that means r1 minus r2. So if we know the distance between the 2 points, we can find out the potential difference between these 2 points. So that becomes the formula in case of uniformly charged sheet. We can further interpret this as this field which we have talked here is a constant or uniform field. Whenever we got a uniform field, we can say potential difference is going to be field into the distance. So potential difference can be written as field into the distance whenever the field is uniform, because that will come out of the integration, right? So, and the distance, this d means the distance between these two, so that refers to d. So we can write in this manner. Moreover, we can also think of, in this case, the field has this direction. So if this is the direction of field, we will say the potential decreases in the direction of field. So that's an important point. When we move in the direction of field, potential decreases. When we move away in the opposite direction of field, potential increases. And if we move perpendicular to the direction of field, there is no change in the potential. We will talk about these terms again. So for uniform case, we can use this. This will be when E vector is uniform, and which we have used here for a sheet. This came out to be our result that could be remembered. Let's take an example in which electric field is given in the form of Cartesian coordinate system. So it says find potential at any point P which has a general coordinates x comma y due to existing electric field, which is 2xi cap plus 3yj cap in SI unit. Also given that potential at origin is 5 volt. So potential of origin is given to us as 5 volt, and we need to find out the potential at any point P which is x comma y. So you can pause this video and solve this, and I'm solving here. So solution should be like this. We can say potential at any point minus potential at origin will be equal to minus integration from origin to that point P E dot dr. Since it is in the Cartesian coordinate system, so we have earlier talked about that it can be fragmented in different coordinates. So this it will be minus integration ex dx, having x coordinate from initial to final, plus integration ey dy plus integration ez dz. Now using this expression, we can simplify this further. V is the potential that we are looking for. V naught is the potential at the origin, which we can write as a 5 is equal to minus. Now this initially, let's put the limit here. This is x variation, right? So x variation is from 0 to x. Limit of y is going to be from 0 to y. Z is not there, so z will run from 0 to 0 because it is only in xy coordinate system. So the last term will become 0. We will have the first two terms. Now ex, definition of ex can be borrowed from here. So I coefficient is ex, which is 2x. So this becomes integration from 0 to x 2x dx, which is easily integrable, plus integration from 0 to y 3y dy. If we use the rules of integration, so this v can be written as transferring 5 that side. This will be 5 minus first term will become x square by 2, and 2 and 2 get cancelled out, so simply x square, and minus this will become 3y square by 2. So this will become answer for potential at any location on the xy plane. So that's our answer. This is how we can use this formula to get the potential if the field is given, which is non-uniform. Here let's take another example in which let's say potential is given and we are looking for field. So it says find field if V is given as, let's say, x squared plus y in proper units. So we know if V is given, how to find E. So there is a formula which is called V is equal to this E is equal to E as a vector. So you can pause and solve. I'm solving over here. So solution is going to be E as a vector is going to be equal to minus del V upon del x I cap plus del V upon del z, or rather dy del y z cap plus del V upon del z k cap. So this is in 3 components form, which we usually write as minus del V or gradient of V. Anyway, these are the partial derivatives. We know how to make the partial derivatives. So in this, if we differentiate, let's try to find this partial derivatives over here. Del V upon del x. When we are going to differentiate this with respect to x, so first term will become 2x, second term will become 0. When we differentiate this with respect to y, then the first term will become 0, second term will become 1. When we differentiate with respect to z, which is absent in this expression, so it will become 0. Using these partial derivatives, this E will be equal to minus, first term will become 2x I cap, second term is 1, so 1 j cap plus 0 k cap. So our answer will become equal to, this E vector is going to be equal to, in that space, minus 2xi minus j. Right, so that becomes the answer. So this is how we can find the electric field if we know the electric potential in that space. Fine. So that's another example. So we have understood the relation between two fields, scalar field and vector field, and we have talked about some certain examples on that. One important point that I'm going to discuss here is since this field E came out to be as minus gradient is equal to minus gradient of V, and we got a relation V is equal to minus integration E dot dr. Based on this, we can interpret that potential this electric field has a direction. This has a direction in which there is maximum drop in potential, maximum decrease or drop in potential. So E is directed in the direction in which the potential drop is maximum. So field has a direction in the decrease of potential. That means if the field is in this direction, so we will say in this direction potential is going to decrease, and if we move against the field, the potential is going to increase. So in the direction of field, if we, let's say this is point 1, this is point 2, we can claim potential of 2 is going to be less than potential of 1. That means if you are moving from 1 to 2, so potential decreases. So 2 has to have a less potential, 1 has to have a more potential. If we move from 2 to 1, potential increases. So in the direction of field, potential decreases. In the opposite direction of field, potential increases. Let's say if we have another point 3 which is perpendicular to the direction with 1, so we can claim potential of 1 is equal to potential of 3. So that another point says in the direction perpendicular to the field, there is no change in the potential. So potential remains constant in the direction perpendicular to the field. It decreases in the direction of field. It increases in the direction of field. So this is another important point that we can remember. This is interpretation of these relations. So you just revise and keep these things in mind. So that's all for this video. Thank you everyone for watching. Have a good time.